All right, you guys, today we're looking more in depth in similarity, and we're looking at segment relationships. So in all of example 1 on this page, I'm saying solve for x in each of the following figures. Simplify fractions or round to the nearest hundredth, so 2 decimal spots. So here in example A, I see 2 overlapping triangles. And since these are marked as parallels, right, I know that these are the corresponding angles that are congruent, and same thing here. So I know that really they're similar because of angle, and it helps me to see how their corresponding parts will link up by drawing them as 2 separate triangles. And by the nature of how they are overlapping, they're going to have the same orientation. So I can see very clearly how my corresponding parts match up. So for the small triangle, I know right now that this side is 5 and this side is 6. I'm sorry, this is 6. And then I know that for my big one, just wipe that away. So for my big one, I know that this full side is x and this full side is 8. Okay, so again, my corresponding sides link up just like their orientation. So if I want to build a proportion to solve for that unknown, I can say that 5 is to x as 6 is to 8. I just like to link it up so that I'm looking at from figure to figure. I read mine from left to right. If you read yours from right to left, that is okay. When you cross multiply, we'll get the same products. So I'm going to make mine 5 is to x. 5 is to x as 6 is to 8. Okay, and then I'm going to cross multiply. So if I cross multiply, I get 6x equals 40. Divide each side by 6. Reduce it down, and we get 20/3. I will take it like that. I will take it mixed. I will take it as a decimal to the nearest hundredth. So here, if I make this mixed, I would say that that becomes 6 2/3. I would take that as 6.67 as well. Either way. And then I usually look back at my picture and I just want to make sure that all of that seems appropriate, right? We're not drawing these perfectly to scale, but it should be reasonable. So as 5 is to x, as 6 is to 8, right? This would be 6 2/3. That makes sense. All right, next up, I've drawn a triangle in the same fashion where I've given you that these are parallels. So these angles would be corresponding. They are congruent, and same here. So I really have 2 overlapping similar triangles. I have the little one and I have the big one. So again, I think it's just a good habit to separate them and draw them as sides of a full triangle. So for my little one, I have a 6 here and a 7 here. And for my big one, this whole side is x plus 6. And this whole side is 9. So if I want to build a proportion and I read it from figure on the left to figure on the right, I can say that 6 is to x plus 6. Just as 7 is to 9. So I've built my proportion. I'm always reading it from one figure to the other, and now I cross multiply. So 7 times the package of x plus 6 equals 54. Okay, from here I can distribute the 7. So 7x plus 42 equals 54. And then take away the 42 from each side. So 7x equals, well, 12. And divide by 7. So x would be 1 5/7. I will take it like that. As a decimal, that would be 1.71 approximately. I will take it like that also, no problem. So simplify your fraction or leave it as a decimal to 2 spots. All right, next up. All right, so looking at C, I see the same parallels, right? I have parallels here. So I know that my corresponding angles would be congruent here and here. So I know that my triangles are again similar by AA, and they have the same orientation. So I'm just going to separate them and draw them as two separate entities. I always draw the small one and then the big one. So for my small one, I know that this part is 10, but it's a little bit trickier getting to here with what was given. So if I'm looking at this full side right here, that full side is 12, and then to get to where my little squiggle is, I'm really taking away x. So this measure right here is 12 minus x. Okay, so I have my small triangle with the sides marked. Now for the big one, I know that this is 14, and this full side is defined as 12. So now that I can see them as sides of a triangle, now I can build my proportion. I can say that 10 is to 14 as 12 minus x is to 12. I'm always consistent in reading it from figure on the left to figure on the right. Okay, cross multiply. So here I have 14 times 12 minus x equals 120. I'm going to distribute the 14. So here I have 168 minus 14x equals 120. Okay, take away the 168 from each side. So negative 14x equals negative 48. Divide each side by negative 14. Okay, and that would simplify to be 24 over 7. I could leave it like that, but if I leave it mixed, I would get 3 3/7. Or as a decimal, I would take it as about 3.43. Both of those options are fine. Okay, next one. Here again, I see those parallels. So I know that my two triangles that are overlapping are similar by AA, and they have the same orientation. So let me draw them out as two separate entities. So for the small one, I have a 7 here and an x here. And for the bigger one, this entire side is 7 plus 4, it's 11. And here is x plus 3. So here, if I build my proportion, I can say that 7 is to 11, just as x is to x plus 3. Okay, cross multiply, and I have 11x equals 7 times the package of x plus 3. Okay, distribute the 7. So 11x equals 7x plus 21. Okay, take away the 7x, and 4x is equal to 21. Okay, divide away the 4, and I get that x is 21 over 4. Okay, I could also make that 5 1/4, or that would be equal to 5.25. So in that one, I didn't have to write an approximation because it was equal to 5.25. So the decimal terminated. I'm not rounding. It is equal to 5.25. All right, next one right here. So here I've drawn it differently, right? We have different parallels now. So if I look at these parallels, let me emphasize them here and here. Then I know that my transversal, if I view this one, would get me a pair of alternate interior angles here. And then over here would be my other pair of alternate interior angles, here and here. So let me mark those angles. Here are alternate interior angles. Here are alternate interior angles. So I can see that my triangles are similar by AA again. I can also mark the vertical angles. They have to be congruent too. I'll give those a triple tick mark. Okay, so in order to see how my corresponding parts align, because here I do not have them with the same orientation, sometimes it helps to darken the corresponding sides and color code them. So here, I'll make these both green. These are both the sides that are in between the double and triple marked angles. Okay, and then I'll darken here, these corresponding sides, I'll make them both blue. They are in between the single and triple tick mark angles. And then my last pair of corresponding sides, I will darken those and make those in red, here and here. So again, what's useful about the color coding is it helps me see how my corresponding parts align. So I can see that if I'm reading it from figure to figure, left to right, 10 is to 18, just as 11 is to x. So that's how I can build a proportion. I don't have this measure right here. I can't build off of it. I could solve for it potentially because I have the 10 to 18 ratio, but I'm only asked for x right there. All right, so building my proportion, I could say that 11 is to x, just as 10 is to 18. Cross multiply, and 10x equals 198. Okay, divide each side by 10. I can just see it as a decimal right now that it would be 19.8. Okay, but as a fraction, that means 19 4/5, or it's equal to 19.8. All right, one more variation here in F. So here I haven't given you any parallels. I've only given you tick marks on the opposite sides. So I can see that even though I don't know its measure, I know that this measure here will match this measure, and this measure. And same thing with what's happening on the right, that I'm breaking this side into 4 equal parts, and the same thing over here. So let's imagine that I just give it a measure. Let's say that I say, well, imagine it that this is 1, like that. And then let's visualize those different overlapping triangles off to the side, separated. So I'm going to draw out those 4 triangles. Okay, what we're going to see, since they all share this common angle right here, they would be similar by side angle side. So I know that for this triangle, if I define this side as 1, this side would be 2, this would be 3, and this would be 4. Okay, and what I know is that this is my x, and this is my 12 that I'm solving for. So I may not know what these parts are as measures, but I know how they are related. I can see that if I focus on this small triangle and this big one, the sides are in a ratio of 1 to 4. So I don't necessarily know that these sides are 1 to 4, but I know the ratio will be 1 to 4. I can build off of that. So I can say that 1 is to 4, 1 is to 4 as x is to 12. Cross multiply 4x equals 12. Divide by 4, and x is 3. So a 3 right here. That makes sense. If I put a 3 here, watch what's going to happen. It's going to move up in increments of 3. This would be 6, this would be 9, and this is 12. So if I went more in depth, I could also start to point out that we have a bunch of mid-segments. So if I block this off for a moment, where I have x, it is a mid-segment with this base of 6. And a mid-segment will always be half of its base. The base will be double the mid-segment. I can see that over here as well. 12 would be the base, where 6 is the mid-segment. So I can see that the mid-segment, again, is half of its base. The base is double the mid-segment. And a mid-segment is just created, if I put a little dot right here, for example, the endpoints of the mid-segment are the midpoints of their respective sides. And for a triangle, it will always have that doubling halving relationship. A mid-segment is half of the base, and the base is double the mid-segment. All right, let's flip it over and look at the flip side. All right, so draw the 3 similar triangles in the diagram. Find each ratio. Okay, so you might see right away that I'm giving you that most common triple right here, that this is a 3, 4, 5. Let me just mark that since I know it right away. Okay, and now it's asking me to draw the 3 similar triangles. Okay, so I know this small one is a 3, 4, 5. 3, 4, 5. Okay, and then this one right here in the middle, right here, this side is 6. This side is 8. 6 and 8. So I can see, oh, well, this triangle right here is really a 3, 4, 5 times 2. So 6, 8, this would be 10. I can put a 10 right here. Okay, and then the big one right here, I can see, well, this whole side right here is 16. And then this whole side right here is 12. I see what's happening, right? My 3, 4, 5, it's really times 4, right? 4 times 4 is 16. 3 times 4 is 12. 5 times 4 would be 20 right here. Okay, but I want to know how these corresponding parts align. So I want to know, well, how is SP, how does that relate to SE? Well, where's SP? SP is to SE. Marking that in red. Well, that's a 3 to 4 ratio. 3 to 4. All right, well, what about SA? Let me pick a different color. How about SA right there? That's 6. How does that relate to SL? Well, that's 6 to 8. And 6 to 8 is 3 to 4, right? So it's still in a 3 to 4 ratio. Okay, how about SR to SK? How are those related? So SR is the full side to SK, that full side right there. Well, SR is 12. SK is 16. It is still a 3 to 4 ratio. So one last ratio. Let's see if it's still 3 to 4. What about PR? So PR is here to here. PR is not a full side of one of those right triangles. So I just want to see, does that hold that same relationship? Does PR to EK maintain that relationship? So PR is 9 and EK is 12. That is still a 3 to 4 ratio. So what I'm seeing then is that these parallels, they divide their respective sides proportionally. It's always in that ratio of 3 to 4. Let me add that here. So parallels divide sides proportionally. And proportionally just means the same ratio. They're all in a ratio of 3 to 4. Okay, so now let's formalize that as a rule. So the side splitter theorem, sometimes we call it the side splitting theorem. So here it just says, well, those parallel lines or segments, they divide the sides of a triangle proportionally. So I know then that A is to C, just as B is to D, just as A plus B is to C plus D. So that's going to give me a shortcut. I don't have to always draw out my two triangles like I did in example 1. I can see that I could build a proportion by saying A is to C, red to red, as B is to D, green to green, as A plus B is to C plus D, blue to blue. So I could build a proportion using any two of those ratios. Okay, but now is a good time to say, well, beware. I'm going to highlight this because this is so important. Beware. That side splitter theorem or side splitting theorem, it does not extend to the parallels. So if I'm solving for the parallel segments here in this diagram, here, I do still have to visualize those two triangles, whether I draw them out or not. Let me draw them out for the sake of example. For the small one, here is A, here is C, here is X. And for the big one, this is A plus B, this is C plus D, and this is Y. So if I want to solve for X or Y, I would have to build off of A is to A plus B, right? A full side of a triangle. Just as C is to C plus D, just as X is to Y. All right, and then one more concept before we do some examples. We have an extension of the side splitter theorem that I alluded to in my example 2. Right? It doesn't have to be just sides of triangles. Here we can extend it. So if we have 3 or more parallel lines, so here we go, here's 3, that are intersected by 2 or more transversals, I drew in 2, then the parallel lines divide the transversals proportionally. And the reason that works is if I extended these 2 transversals, eventually they're going to cross. And I can picture this as a larger triangle, even if it is not drawn as such. So we know that our parallels will divide their respective sides proportionally. So I know that the measure here, AB, is to the measure here, PQ, just as the measure here, BC, is to the measure here, QR, just as this full measure here, AC, is to this full measure here, PR. Let me write that out. So AB is to PQ, red to red. Just as BC is to QR, blue to blue. Just as AC is to PR, and that is green to green. So I'm just syncing up my corresponding parts on one side to the other, and I typically read from left to right, so left side to right side. All right, so now let's do a few examples. All right, so in example 3, solve for x in each of the following figures, simplify fractions, or round to the nearest hundredth. So I can use that side splitting theorem now. So if I'm looking at corresponding parts, I can say, well, 6 is to 8, just as this full measure, 13, is to what I want, which is x. All right, so if I go 13 is to x, I'll start there. 13 is to x, just as 6 is to 8, right? I can build off that proportion. So cross multiply, and I have 6x equals 104. I can divide away the 6, and I can get that x is 52 thirds. As a mixed fraction, that would be 17 1/3, which is about 17.33 or 17.3 recurring. That is fine. All right, next up. This one is the extension of the side splitter theorem. So I'm just linking up my corresponding sides. So x is to 6 as 10 is to x. Okay, build a proportion. So x is to 6 as 10 is to x. Okay, cross multiply, and x squared equals 60. Okay, solve by taking the square root. Okay, I want to simplify the 60. I know that's 4 times 15, so I'm going to get plus or minus 2 root 15. Now remember, I can't have a negative measurement in my geometry world, so it has to be the positive 2 root 15. Okay, we leave our answers as simplified radicals if it's appropriate. All right, next up, a little bit more algebra here. So again, I can use my side splitter theorem. I can say that right here aligns to right here, and then here to here. So building my proportion, I can say that x plus 5 is to x plus 2, just as x is to x minus 2. So here I'm cross multiplying, so I have x times x plus 2. And then over here, I have x plus 5 times x minus 2. So on the left, I'm going to have to distribute the x. So x squared plus 2x. And on the right, I'm going to have to FOIL it. So my first is x squared. My outer minus 2x. The inner is plus 5x. And that last is minus 10. So let me clean that up. I have x squared plus 2x equals x squared plus 3x minus 10. So here, when I try to consolidate, if I subtract x squared from one side, it's going to go away from the other side also. So it becomes really a linear equation. 2x equals 3x minus 10, right? The squared part, x squared, went away. So now I can take away 3x from each side. So negative x equals negative 10. Divide each side by negative 1, and we get that x is 10. Okay, let me just double check that that makes sense. Let's say I plug it back in. That would give me a 15 right here and a 10 right here. Okay, this would be a 12, and this would be an 8. All right, so is 5 to 12 the same as 10 to 8? Yes, it would simplify to a 5 to 4 ratio. So I've done my job, I've solved, and I got x is 10. One more. All right, so again, I can use my shortcut. I can use the side splitter. So I can see that right here, x minus 3 is 2x, as 1/3 of the package x plus 1 is to x minus 4. Okay, so let me build that proportion. So x minus 3 is to x, just as. And I'm just going to distribute that 1/3 to make my life easier. So 1/3 x plus 1/3 over x minus 4. Okay, so now I can cross multiply. I have x times 1/3 of x plus 1/3 equals x minus 3 times x minus 4. All right, so I need to distribute the x right here over both of those items. So I have a third of x squared plus a third of x. On the right, I have to FOIL it out. So I have x squared minus 4x minus 3x plus 12. All right, I'm going to combine my like terms. So a third of x squared plus a third of x equals x squared minus 7x plus 12. Okay, I have a fraction. I don't like a fraction. I don't think many people do. So I want to resolve that. I want to clear it. So if I see a 1/3, my way of clearing that is to multiply by 3, by the reciprocal of 1/3. So I'm going to multiply every single term by 3, and that preserves the balance of my equation. So right now I have x squared plus x equals 3x squared minus 21x plus 36. Phew, that looks a whole lot better. So now I want to pull everything to one side. I want my equation set equal to 0. So I'm going to take away the x squared and the x. So 0 equals 2x squared minus 22x plus 36. Okay, so when I run through my list of things to do for factoring, my very first thing to do is look for a GCF. Do I have a greatest common factor? I do. It's a 2. So here I'm going to divide out that 2. And what's left behind is x squared minus 11x plus 18. So now I'm looking for two numbers that multiply to a positive 18 that add to a negative 11. That 2 has already been factored out. All right, so again, multiplies to a positive 18 but adds to a negative 11. Should be minus 9 and minus 2. So when I solve, I get a solution at 9 and at 2. So I have two possible options. But if I plug that 2 back in, look at what happens here. 2 minus 3 would be a negative 1. It would give me a negative measure for this side right there. And we know that that is just not possible. So this one is out. So x must be 9, but let's just double check that that makes sense. Right, 9 minus 3, that would make this 6, and this would be 9. Okay, over here, if I plugged in 9, a third of 10 would be 3 1/3. And 9 minus 4 would be 5. So 6 to 9 would be 2/3. 3 1/3 to 5 would also be 2/3. So x is 9. We solved for it. We got it. We are done. X is 9. All right, that's all I got. Have a good rest of your day.